Mount St. Helens in Washington state is one of the most well-monitored volcanoes on the planet.
On May 18th in 1980, it exploded in a volcanic display never before witnessed in modern times.
Deep beneath the rugged slopes of Mount St. Helens, something is stirring once more. What scientists have just found happening inside the infamous volcano has them sounding alarms. Not in reactionary fear, but out of sheer concern born from decades of intimate study and cautious surveillance. Mount St. Helens, long known for its catastrophic 1980 eruption that obliterated landscapes and claimed lives, has begun to exhibit a series of highly unusual and accelerated geophysical changes that signal a potential shift in its volcanic behavior. These changes are not subtle. They are happening deep in the earth, and they are happening quickly. Before we start, please don't forget to like and subscribe to our channel for more updates. The initial red flags began with an uptick in seismic activity, a frequency and intensity of small earthquakes that was markedly different from Mount St. Helens' usual background rumblings. Typically, seismic swarms in volcanic regions can be attributed to minor movements of magma or tectonic shifts, but in this case, the quakes were deeper, sharper, and far more numerous than anything recorded in the past decade. They weren't just clustered around the summit either. They were radiating outward in strange patterns, creating an underground map that puzzled and unsettled the scientific teams monitoring the volcano. Seismic data began showing clusters of earthquakes as deep as 20 kilometers below the surface, extending well into the upper mantle. That in itself was alarming. Most shallow quakes caused by volcanic activity are centered in the crust, typically no deeper than 5 to 10 kilometers. But this time, the magma was coming from much farther below, indicating a potentially massive recharge of the volcanic system. This recharge isn't just a simple bubbling of molten rock. It is a full-on pressurization of the volcanic plumbing system, a reawakening of a sleeping geological giant. Even more unnerving was the speed at which the magma seemed to be moving. High-resolution data from GPS stations planted around the mountain began showing subtle but continuous uplift. The ground was swelling, not uniformly but with localized bulges indicating intense underground pressure points. This inflation of the surface could mean that magma is not only rising, but also pooling in new chambers beneath the volcano, chambers that didn't exist or weren't previously detected. This redistribution of magma suggests the volcano is reorganizing itself in ways that are not yet fully understood. Satellite-based remote sensing added another layer of concern. Thermal imaging revealed warm spots across the caldera and surrounding flanks, areas that should not be radiating that much heat. These thermal anomalies were not visible to the naked eye but were stark in the infrared spectrum, signaling increased geothermal activity. Combined with sulfur dioxide emissions, which have spiked intermittently in recent weeks, the signs point toward a volatile system gearing up for a possible eruptive phase. The atmosphere above the mountain is beginning to bear chemical fingerprints of fresh magma, which means gas is escaping, pressure is building, and the system is becoming increasingly unstable. Subterranean soundings using muon tomography, a technique that uses cosmic particles to peer through solid rock, have painted an even more vivid picture. Deep inside Mount St. Helens, voids are forming and filling rapidly. These voids are magma pockets, and their rapid formation is atypical. Normally, these chambers evolve over many years. The current pace is swift and erratic. That kind of behavior is unprecedented in recent geological history for this volcano and is causing geophysicists and volcanologists to reevaluate long-standing models of how this mountain behaves before an eruption. Adding to this unease is the discovery of unusual chemical signatures in groundwater samples taken from the surrounding region. Elevated levels of certain trace elements like tellurium and molybdenum suggest that magma is interacting with the crust in new and more chemically active ways. These elements are often carried in high concentrations by volatile-rich magmas, the kind capable of explosive eruptions. Such signatures are rare and usually not detected unless magma is intruding aggressively into new rock layers, breaking bonds, releasing gases, and dissolving minerals. What makes all this so startling is the convergence of multiple lines of evidence. It's not just one signal pointing toward unrest, it's a chorus. Seismic activity, ground deformation, gas emissions, Thermal anomalies and chemical shifts are all spiking at once. And perhaps most unnervingly, this is happening in a compressed time frame. Historically, such signs unfold over months or years, giving scientists time to observe and model the changes. This time, things are unfolding over weeks. There's also growing concern about the scale of the system that seems to be involved. Mount St. Helens isn't isolated. It sits within the Cascade Volcanic Arc, a geologically active zone linked by deep magma reservoirs and fault lines. Satellite gravimetry has shown that these deeper systems are also in flux, with mass redistributions that suggest Mount St. Helens may not be the only volcano recharging. The possibility of a chain reaction, while still speculative, has researchers worried about systemic pressure building beneath the broader region, potentially activating other volcanic centers. This interconnectedness is part of why scientists are so concerned. Mount St. Helens may be the epicenter of current activity, but its behavior could influence, or be influenced by, the deeper volcanic network of the Cascades. That means the implications stretch far beyond the immediate vicinity. If the magma systems are linked, then stress in one part of the arc could destabilize others. In effect, Mount St. Helens could be the first domino. What's also being reconsidered is the composition of the magma itself. Petrological analysis of recent ash deposits from minor steam events and fumarole activity suggests a higher than normal silica content. High silica magma is sticky and gas-rich, making it more likely to erupt explosively rather than flow benignly. This compositional shift, if accurate, means that when an eruption does occur, it could be significantly more violent than the dome-building events of the 2000s or the relatively moderate emissions of steam and ash seen since. To complicate matters further, weather patterns and seasonal changes are influencing surface water levels, which can interact with subterranean systems in unpredictable ways. Melting snowpacks and increased rainfall have seeped into the volcano's edifice, potentially infiltrating hot zones and triggering phreatomagmatic reactions. When water meets magma, the result is often violent. Explosions can be magnified and steam-driven eruptions can precede or even trigger larger magmatic events. These interactions are notoriously hard to predict, yet they're now a real possibility given current conditions. The terrain itself is also showing signs of structural weakness. LiDAR scans have detected subtle shifts in slopes and ridges, indicating slow landslide motion. If a flank of the volcano were to collapse, especially under the stress of magma intrusion, it could act as a rapid release valve, depressurizing the system and allowing for an abrupt eruption. This is exactly what happened in 1980, when a massive landslide preceded the catastrophic lateral blast. The eerie similarities are not lost on those who study these processes. History may not be repeating itself exactly, but the echoes are impossible to ignore. There's an inherent danger in the unpredictable behavior of volcanoes like Mount St. Helens. They don't follow a script. They don't provide neat timelines. Scientists can model probabilities and suggest likely outcomes, but when a volcano begins to behave in unfamiliar ways, all bets are off. The recent findings at Mount St. Helens have upended assumptions about how long it takes for pressure to build, how magma migrates, and what the precursors to eruption might actually look like. It's as if the mountain has decided to rewrite the manual, and researchers are scrambling to keep up. None of these developments can be dismissed as routine. The instruments don't lie. They are detecting a cascade of changes: deep tremors, rapidly ascending magma, rising heat signatures, escaping gases, shifting ground, and chemical mutations. Each alone would merit increased observation. Together, they point to a system that is accelerating towards something, though exactly what that something is remains cloaked in uncertainty. The pace is what's most troubling. Volcanoes often give clues, but this time the clues are compressed, ambiguous, and increasingly intense. What makes this more than a scientific curiosity is the risk to life and infrastructure. Mount St. Helens is surrounded by communities, waterways, and ecosystems that could be devastated by a major eruptive event. While the volcano is in a remote region by urban standards, it is still within reach of major transportation corridors, hydropower systems, and agricultural zones. The ash cloud from an explosive eruption could disrupt air travel, damage machinery, contaminate water supplies, and blanket crops. Lahars, volcanic mud flows triggered by melting snow and ice, could race down river valleys with terrifying speed, wiping out everything in their path. Then there's the psychological weight of the unknown. For many, Mount St. Helens is a symbol of both nature's fury and resilience. People remember the haunting images of the 1980 eruption, the sideways blast, the blackened skies, the flattened forests. The idea that the mountain could be gearing up for something as significant, or even more so, is deeply unsettling. It brings into focus how little control humanity has over Earth's internal forces, and how quickly entire landscapes can be transformed. Every day that passes with this level of activity deepens the urgency. Researchers are working around the clock not just to gather data, but to interpret it, to model the possibilities, and to advise emergency response teams. They're not panicking in the emotional sense, but there is a growing scientific panic, the kind that comes from staring at a pattern that's never been seen before and realizing it might be the beginning of something unprecedented. They've seen the warning signs, and now they are waiting for the mountain's next move. Mount St. Helens is speaking, not in words but in tremors, in heat, in gas, and in the slow, steady rise of Earth beneath the feet of those who monitor it. It is a language scientists have spent their careers trying to understand. And now, as the signals grow louder and more erratic, they are confronting the very real possibility that the volcano is entering a new phase, one that may defy past patterns and exceed past eruptions in scale and unpredictability. Whatever is happening beneath Mount St. Helens is not just another episode in its long history of volcanic behavior. It is something different, something more dynamic, more immediate, and more uncertain. The convergence of deep seismic unrest, magma surge, chemical transformation, and structural instability is not just a confluence of anomalies, it is a red flag rising over the Pacific Northwest. The mountain is alive in ways that haven't been seen in decades, and its reawakening may just be the beginning of a larger story waiting to unfold. The revelation of Mount St. Helens' accelerating internal changes has created a ripple effect far beyond the scientific community. As the instruments embedded in and around the mountain continue to relay real-time data that suggest an increasingly volatile state, agencies and experts across disciplines are reconfiguring their understanding of what such activity could imply. The data points to something far greater than a localized magma movement. It speaks of systemic change, a restructuring of the mountain's geophysical core. This shift is subtle in some respects, but profound in its implications, suggesting that Mount St. Helens is undergoing a transformation, one that is redefining its behavior, potential eruption style, and even its long-term threat profile. While much of the initial attention has focused on the indicators from seismic and thermal readings, more nuanced studies are beginning to emerge, studies that delve into the magnetic and gravitational changes occurring around the volcano. Magnetic field measurements have revealed disruptions beneath the mountain's edifice, deviations that may suggest the introduction of fresh, iron-rich magma into layers of rock that previously held little such material. These shifts in the magnetic landscape are not merely academic anomalies. They often precede structural adjustments in volcanic conduits, hinting at realignment or even the formation of new eruptive paths. Complementing this are alterations in local gravity. Tiny changes in gravity readings, measured through gravimetric sensors, have shown that mass is accumulating beneath Mount St. Helens at rates not previously observed. The mass in question isn't simply magma. It includes volatile-laden fluids, semi-molten rock, and mineral-rich gases, all of which contribute to building pressure and changing the internal architecture of the volcano. Gravity anomalies, when they spike like this, have historically been associated with explosive eruptions elsewhere on the planet, such as in Indonesia or Chile, where magma chambers swell rapidly, breaching thresholds that lead to sudden decompression and eruption. At the same time, something curious is happening in the crustal structure surrounding the volcano. Rock mechanics experts have reported microfracturing events, essentially tiny ruptures in the crust, that appear to be both more numerous and spatially unusual. Instead of following the predictable radial or concentric patterns typical of magma intrusion, these microfractures are forming erratically. This suggests that the magma isn't moving through existing channels, it's forcing new paths, pressurizing rock in directions previously deemed geologically improbable. These new paths may bypass older eruptive vents and could potentially create new ones, altering the topography of Mount St. Helens and expanding the zones of risk for future activity. There is also an emergent consideration of geothermal feedback loops occurring deep within the mountain. As magma rises, it heats subterranean water tables, which in turn increases steam generation and fracturing. These interactions are now being modeled as amplifiers of instability, particularly in scenarios where pressure builds faster than it can be released. The danger here lies in the possibility of a cascading feedback system. Rising magma heats water. Water fractures rock. Fractures allow more magma to rise, and the cycle repeats with increasing ferocity. This could lead to sudden overpressure conditions that result in explosive ejections of ash, lava, and pyroclastic material. Furthermore, high-resolution geological modeling has uncovered previously undocumented sills, horizontal intrusions of magma, that could act as ticking time bombs. These sills are deep layered pockets of magma that can become hyperpressurized when sealed off. If breached, they could discharge enormous volumes of molten material in a matter of minutes. The presence of multiple sills, especially ones forming at varied depths, indicates a complexity that was not accounted for in earlier risk models. Mount St. Helens may not just erupt from the central vent. It could vent laterally through flank eruptions or even secondary craters, increasing the difficulty of forecasting where and how an eruption could manifest. On the surface, ecological indicators are also shifting, and while they may seem subtle to the casual observer, they speak volumes to those attuned to environmental patterns. Certain plant species that are sensitive to soil temperature and gas concentration have begun to alter their growth behaviors. Some have wilted prematurely while others are flourishing out of season, a sign that subsurface heat and gas composition are changing rapidly. This kind of biological response has served as a precursor in other volcanic regions, where flora reacted to geochemical changes weeks before any eruptive activity. Animal behavior has shifted as well. Birds and small mammals that once nested along the volcano's ridges have begun migrating away. Seismologists often joke that animals can feel it before we see it, but there is increasing interest in studying these patterns scientifically. Motion sensor data collected by remote cameras show declining activity in once populated zones, and radio-collared elk and deer have changed their migration patterns. It's subtle, but the timing aligns too closely with underground changes to be dismissed as coincidence. Looking at the skies, another line of observation has become more vital than ever: atmospheric analysis. Scientists are now deploying high-altitude drones to monitor gas release rates in real time. These UAVs collect data on sulfur dioxide, carbon dioxide, and other volcanic gases. The results have been disconcerting. CO2 levels in particular have shown sudden episodic bursts, short spikes that indicate magma degassing at high velocity. These types of bursts typically signify magma very close to the surface. Combined with increasing sulfur output, this points to a volatile environment where gas cannot escape quickly enough, meaning pressure is mounting with limited outlets. Even the sound of the mountain has changed. Infrasound microphones, devices that pick up ultra-low frequency sounds below the threshold of human hearing, have recorded pulsating harmonic tremors. These aren't traditional earthquakes, but rather continuous rhythmic signals produced by magma movement and gas flow. When harmonic tremors intensify and sustain over time, they have often been tied to imminent eruptions in volcanoes across the globe. These deep resonating sounds speak of a subterranean pulse growing stronger, more insistent. Meanwhile, deep borehole temperature sensors have reached record highs in recent weeks. These sensors, placed at multiple depths and spread across key regions of the volcano, provide critical insights into heat flow. A consistent temperature rise, especially in boreholes that previously remained stable for decades, is a signal that something new and massive is generating heat from within. It's not a spike that corresponds with seasonal temperature changes or climate variations. This is geothermal heating of a scale that could only come from intense magmatic intrusion. Advanced modeling software, incorporating all these parameters, thermal readings, seismicity, gas emissions, and crustal deformation, is now producing results that many researchers hoped they'd never see. The predictive outputs are converging towards scenarios that involve rapid onset eruptions with minimal surface warning, Unlike the 1980 eruption, which had days of escalating activity, some current models suggest that a violent eruption today could occur with as little as a few hours of obvious surface signals. That window, terrifyingly small, changes how emergency planning must be conducted. Regional planning committees are already being briefed with provisional data, and simulation exercises are being ramped up to prepare for worst-case scenarios. Evacuation protocols, which previously allowed for 48-hour execution, are being revised down to accommodate a much faster response time. The communities closest to Mount St. Helens have lived with the volcano's threat for decades. But this new activity profile may require a level of readiness more akin to active volcanic zones in Iceland or the Pacific Ring of Fire. Infrastructure risks are also under evaluation. Dams, bridges, and transportation routes located downstream or adjacent to the volcano are being reassessed for their structural resilience in the event of a lahar or pyroclastic flow. There is a particularly high concern for rail lines and pipelines that intersect the potential flow paths. Any eruption could cause severe secondary disasters if critical infrastructure is compromised, especially energy lines or water reservoirs. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on Mount St. Helens activity? We want to hear from you. Thank you for watching, and see you next time.